Let's solve exponentials first. So an exponential equation is when you're solving for an exponent, and then your property of equality says that if b is greater than 0 or b doesn't equal 1, then if you have two bases being raised to an exponent and the bases are the same, then that can only be true if the exponents are the same. So if you have like 7 to the third power is equal to 7x, well then x has to equal 3, that sort of thing. We do it a little bit more complicated. So here, the variable is an exponent, so x is an exponent. One thing that you try to do is you try to rewrite the base, the bigger base, as a smaller base. So 8 can be written as 2 to the third power. So you have 2 to the x is equal to, and then that 8 we're going to replace with 2 to the third. Still raised to that fifth power that was there. So now by your exponent rules, this is 2 to the x is equal to 2 to the 15th. Therefore, x has to equal 15. Let me show you another example. Here I have two bases. They are different, but the base of 9 can be written as 3 squared. So if I rewrite 9 as 3 squared, raised to the 5x plus 2 is equal to 3 raised to the 6x. Exponent rules say that if you have a power to a power, you're going to multiply them together. So we're going to multiply these two together. So this is 3 raised to 10x plus 4 is equal to 3 raised to the 6x. Now that your bases are the same, you can say, hey, actually, these two exponents have to be equal. So we set up a little equation, 10x is equal to 10x plus 4 is equal to 6x, and then we're just going to solve that. So subtract the 10x from both sides. We get 4 is equal to negative 4x. Divide by that negative 4, and x is equal to negative 1. Just like any other time that we solve, we could take that and plug it back in. So you could plug it back into the x here and the back into the x here and verify that your answer is correct. But that's one thing that we can do with our exponents when the variable's in the exponent to solve them. All right, so what do we do if you can't write the exponent, the base of one, as the other one, and the exponent is what we're solving for? So if both sides of the equation cannot be written as powers of the same base, you're going to introduce a log. So here we first check, hey, can I write 19 as 4 to the power of something? Or even like 4 is 2 to the second. So could I write 19 as 2 to the something? No. So if we can't do that, then we just introduce our log. So this is going to be log base 4 of 19. So base 4 of 19 is equal to x. And then you can evaluate this in your calculator. So log 19 over log 4. Pop that into our calculator, and we get x is equal to 2.124. I would pause and see if you can do the next 3. They increasingly get harder. So I'd pause here, try the next 3. All right, so again, we have this variable. It's in the exponent. We can't rewrite 3 as to 15 as 3. So we're going to introduce our log. So this would be log base 3 of 15 is equal to x. Since we both have the base and what we're taking the log of, you can use change base formula. So log of 15 over log of 3 is equal to x. Throw that in your calculator, and you should get 2.465. Here, we have e being raised to the power of x. So if we want to be able to introduce a log, we're going to have that isolated. So we're going to divide both sides by the 5. So e to the x is equal to 23 over 5. We're going to introduce our log. So log base e of 23 over 5 is equal to x. Remember, log base b is natural log, so we can put natural log of 23 over 5 into our calculator. Make sure that we are either using parentheses around the 23 over 5 or we're using our fraction button. And we get 1.526. All right, and then lastly, the most difficult one. Here we have a base of 5 and a base of 3. Can't rewrite them as each other. So we'll introduce the log. So here we have log base 5 of 3 to the power of x minus 1 is equal to 2x plus 3. So this base raised to all of this is equal to all of that. Okay. Don't change what you're doing just because it's more complicated. We'll figure out the complicatedness. So the part that makes this a little bit hard is right here we have that exponent. But we have our rules that say, hey, that exponent can come out front. So we have x minus 1 times log base 5 of 3. Log base 5 of 3 we can evaluate. We can put in our calculator with change base form. So I'm going to do that. When I put that in my calculator, I get 0.683. And then it's just a linear equation. So you're going to distribute your 0.683. You're going to minus the 0.683x, and then minus the 3 from both sides. So we get negative 3.683 is equal to 1.37x, and then divide both sides. And I got negative 2.79. So if you can, when you have the variable and the exponent, if you can, make them the same base. You want to, because that's the easiest way. But if you can't, then you got to isolate that base and then introduce your logs. Now let's solve log equations. All right, so what if we have one log? What if we're solving for the log? So now, instead of missing an exponent, we don't know what we're taking the log of or what the base of the log is. So if you have one log, we're just going to put it as an exponent. We're just going to do the reverse of what we just did. So 36 raised to the 3/2 power is equal to x. We can then evaluate that. You can throw it in your calculator. You can take the square root of 36 and then cube it, and you should get 216. I would pause, try these other 3. They're all a little bit different, but pause the video, try the other 3. Here we have log base 9. So 9 raised to the 3/2 power is going to be equal to x. So that means the square root of 9 to the 3rd power, so 27. Here we have 16 raised to the 5/2 power is equal to x. So the square root of 16 is 4. And then 4 to the 5th power is 1024. And then lastly, we have x raised to the 3rd power is equal to 8. So we kind of have to think, what number to the 3rd power is equal to 8? You can do a little guess and check. But most people recognize that it's 2. So 1 log. Well, what if we have 2 logs? All right, well, if we have 2 logs, it's actually pretty easy. It's the easiest one, most people think. If you have 2 logs, we have this rule that says if the base of the logs are the same, then what we're taking the log of has to be the same as well. If it's not, they're not the same. It's equal though. All right, so here we have log base 2. That's the same as log base 2 of what it's equal to. Because those are equal, x squared minus 4 is equal to 3x. So we can set x squared minus 4 equal to 3x. Well, that's a quadratic. So you know how to solve a quadratic. So x squared minus 3x minus 4. Check for factorability. So do we know any numbers that multiply to -4, but if I add them together, I would get -3. Hopefully you came up with -4 and +1. So x is equal to 4, and then x is equal to -1. Okay, but we're not done. So the problem that can happen is when we're taking a log, we have to be taking the log of a positive number. So I always have to check for extraneous solutions. So if I take -1 and I plug it back in here, do I get a positive? 3 times -1 is -3. So even though we got this answer when we calculated, this number is actually extraneous. Because when we plug it back in, it's giving us a negative. Try the other one. So we take 4, plug it back in. 4 times 3 is 12. So that's positive. I'm going to check this one, this log as well. 4 squared is 16. Minus 4 is 12. So that gives us a good number, a positive number, not a good number. So our answer is just x is equal to 4. Okay, there's 3 more. I'll put the answers here for you. If you have questions or you're not getting those answers, let me know, and then we can go over them in class. So you should try these. You should have some work. This one is extraneous. And then on the next page, I don't know, my notes just went crazy. On the next page at the top, we have x is equal to -2. Excuse me. X is equal to -4. Nothing's extraneous there. And then this last one, we get x is equal to -3. So if your bases are the same and your logs are set equal, you can just set the thing that you're taking the log of equal. All right, so then we have the last thing, is what happens if we have more than one log on one side of the equal sign? If we have more than one log, we want to use our condensing rules to bring those logs into one log. We want to take it back to either when a log is equal to a log, and then we set the stuff equal, or when we just have one log that we can use put it into exponential. So we'll do some examples for you. I do have a typo here in this one, this 4. I apologize, should be a 6. All right, so let's start out with taking a look at how many logs we have. We have 2, and they happen to be on the same side. So I'm going to use my condensing rules to bring these together. So that means that I would have log base 6. Because I'm adding, I would be multiplying a and b together, or what I'm taking the log of together. So I can actually multiply x plus 8 times x minus 8, so I would do that. So I get log base 6 of x squared minus 64. I'm keeping it in parentheses because I'm taking the log of that whole thing is equal to 2. Now that I only have one log, I can go exponential. So 2 to the 6 to the second power is equal to x squared minus 64. And then I can solve that. 6 squared is 36. I can isolate that x squared by adding 64 to both sides. we get x squared is equal to 100. So I can take the square root and I get positive 10 and negative 10, or plus or minus 10. I'm writing them separately in case I get an extraneous solution when I plug them back in. So if I plug 10 back here, I get 18. If I plug it back here, I get 2. Both of those are positive. No worries on the positive 10. If I plug negative 10 in here, I get a negative 2. Extraneous. Don't even need to check the other one. It's extraneous in the first one, so it's going to be extraneous. It might be extraneous in the second, but it doesn't matter because it's already extraneous once. All right, let's take a look at this one. So here I just have that 1 log. When I have 1 log, I use exponential. So log, remember this is base 10 when the base is not written. So if I put this in exponential, this is 10 squared is equal to 6x minus 8. 10 squared is 100, and then you can solve, you should get 18. Okay, it's really about how do we get rid of those logs? So let's go down. Here I have 2 logs on one side. I have a log base 2 of 3x plus 10 minus log base 2 of x is equal to 3. So how do I condense this when it's subtraction? How do I condense my logs when it's subtraction? I use division. So this is log base 2 of 3x plus 10 over x is equal to 3. I was able to get this down into 1 log. That's great, because now I can use rewriting in an exponent to help me. So this is 2 to the 3rd is equal to 3x plus 10 over x. 2 to the 3rd is equal to 8, so I'm just going to replace that with the 8. And now I can multiply this side by x to cancel out the denominator. I can multiply this side by x to cancel out the denominator. That's going to give me 8x is equal to 3x plus 10. I can minus the 3x from both sides. Divide by 5. And x is equal to 2. Okay, I'm going to encourage you to try those other 3. I do have another typo here. This should also be a 6. Okay, good time to pause the video. Try the problems. I'm going to give you the answers right now. So here for this one, I'm going to condense them. I'm going to have a quadratic that I'm going to solve. It is factorable. I got x is equal to negative 9. X is equal to 4. But x is equal to 9 was extraneous. The one below, you had to use your power rule where this comes up as an exponent. You're then the same thing as the square root of 25, so it's just 5. When you condense here on the left, you get 1 log on the left, 1 log on the right. So that's when I'm using that property of equality that says 5x and 20 are equal to each other, and then you can solve. And then the last one, we're going to condense these guys, and it's division. Rewrite it as an exponential. I got to do a little solving, and I got x is equal to 3. Final answer. All right, so those are the notes on how to solve a log. Your goal when there is more than one is to get it back to 1 log on each side. Or if you're condensing and there's not a log on one side, then just condense it down to 1, then exponential.